Hi everyone, this is Mr. Gunnell again, and today our lesson is looking at our fourth lesson in the simple harmonic motion topic, and we're looking at the energy and period of springs. You'll also see today that I have up the physics data booklet. We're going to be working in a couple of sections. You can see topic 4.1 there on oscillations. We only have one formula, it's T equals 1 over F, but we're also going to look down into topic 9 and subtopic 9.1, which is where most of our work is going to be. And you can see that some of the equations we've already looked at are over there. So let's jump into the lesson. We're looking at the interchange of kinetic and potential energy in simple harmonic motion, and then describing how those changes will happen. And there are a couple of homework questions for you guys to look at on page 359. So I'm going to start this out by looking at some things from previous lessons in this Do Now. So you should maybe take a second and pause the video and try this question. And hopefully you have taken a second to do that. What we're going to do is look at a few different locations. We want to label a place where the acceleration is at a maximum. Since this is a graph of position versus time, I'm going to go ahead and label anywhere that the position is a maximum, the acceleration should be a maximum also. You only really need to label one, but there are three locations in this graph. There's a spot right there where the acceleration is a maximum. There's a spot here where it's a maximum, and here where it's a maximum. And again, that's because the acceleration and the displacement are supposed to be proportional. So when there's a lot of displacement, there's a lot of acceleration. Now, when we're labeling the place where the velocity is at a maximum, that's going to be as the object's passing through the center or passing through its equilibrium location, because that's the point where there's no acceleration because it's at equilibrium, but it is moving the fastest. And I'm going to label that V or that V. The next part that we're looking for is a general equation. And all we have to really do with that is just write our formula for position. We need to identify what type of graph it is. There were no values on the x-axis, so we're just going to call that x naught as its maximum. And then this looks to me like a cosine graph, and it's a positive cosine. So we're just going to say cosine, and then remember always inside is the omega times t. And you can see that these equations are actually no secret. They just expect you to understand which graph you're looking at. So if you look at the data booklet reference over here, we get two options. We get x equals x naught sine of omega t, or x equals x naught cosine of omega t. They will expect you to know if it's flipped, so you're going to have to throw a negative in there if it's a negative graph. But each of those relates to an equation right below it, which we're going to use for the next part of this question. So they want a general equation for the velocity. Now, since we're dealing with the cosine equation for x, we're going to be dealing with the one directly below that, which is v equals negative omega x naught sine of omega t. I mentioned a lot of derivatives in the last class, the last lesson that we looked at, but again, that's really not necessary because they're given both to you in the data booklet over there. All right, so let's get into today's lesson. We're going to look at different locations where things are maximum and minimum. And so I picked a spring mass oscillator. We're going to assume that it's just going back and forth between these two extremes of over here, x naught. We can call this side negative x naught. And then right in the middle, we have equilibrium. My drawing could have been better. That should be symmetrical. But it's going back and forth between those two extremes. So I wanted to look at when each of these different values is the most. So I listed out over here a list of all the variables we could deal with so far. And so the x isn't really too surprising. X is a maximum because you're at a maximum distance. So there's a maximum at either end, and there's zero position at the middle, because we call that just the equilibrium, and that's where x is 0. So on the left, it's negative x naught, and on the right, it's positive x naught. Now, since it slows down and stops at the ends, we're going to say that there's, actually put units on this, there's no velocity at the ends because it has to turn around, and it's got to stop in order to do that. But the velocity is, again, a maximum when they're in the center. And again, because we're connecting acceleration and position, they should be proportional to one another. If you've got a lot of position, you've got a lot of acceleration. So that's going to be a maximum at either end. If we think about springs, it's going to be the most acceleration when the spring is most stretched. Or if we think about the force, the spring is applying the most force at the ends. And since it's at equilibrium, we would say that there's no force from the spring, so there's no acceleration in the center. When we look at the kinetic energy portion of this, kinetic energy is related to velocity. So since it's not moving at the ends, we would say there's no energy at the ends, and there's the most kinetic energy in the middle. So it's going to be a maximum there. And we're going to look soon at the formula for that. And then potential energy for a spring is based on displacement. So we're going to have the most energy, or most potential energy at the ends, just like with position, and no potential energy in the middle, or no spring potential energy anyways. There will be obviously kinetic energy in the middle, but the potential energy is maximum at the ends. Okay. When we want to look at equations for the maximum either position, velocity, and acceleration, we can really kind of go with those equations we've been dealing with already and just look for when they become a maximum. Now, all of these are related somehow to a sine or a cosine. And we know anytime we take a sine or a cosine, the highest possible value we can get is 1 or negative 1. And so all that means is that if we're looking for the maximum numbers for any of these, if I look for the x max, we already have a name for that. We call that the amplitude. That's just x naught, because if I get a high or a low value of positive or negative 1, the sine part's just going to not really matter, because at the maximum it's just going to be 1. Now the same thing for velocity. If I'm looking for Vmax, that's just omega x naught. The highest value for cosine is also 1, or negative 1. And we're just looking for amplitude really. And then Amax is going to be, now in this formula it's a negative omega squared x naught. Like I keep mentioning, it's either positive or negative, so we're looking for the maximum magnitude, would just be omega squared x naught. And again, we can think about the direction within the actual question, but when we're looking for maximum, these sines and cosine parts don't really matter, and we just take whatever's out front. And so we should always be thinking about when they're asking for the maximum values that we can use any of these three formulas. Now those are going to be useful in a minute, but first what we need to look at is how to find specifically the period for a spring mass oscillator. Now this is not really a secret. The IB is going to give it to us down here in this mass spring period formula, and we get 2 pi radical m over k. So I want to talk about how we're going to get to that. So the easiest way to think about this is if we take this mass and we displace it out to the side. So somebody takes and pulls it, and they're going to put it out there, and then they're going to release it. So we've got a displacement over to the right, which means that it's going to accelerate back to the left once it's released. Like I said, the best way to think about this is with forces. And so if we imagine all the forces that are acting on that, we're going to get, once it's released, really only 3 forces. We have some gravity, we have some normal force, and then the spring is going to be pulling back towards the center. So we got some Fs. And if you also remember back to when we were dealing with drawing forces, the most common thing we did is we would take a look at Newton's second law. And that's F net equals ma. In our diagram, the gravity and the normal force are really just going to cancel out, so our net force is really just the spring force. And so then we can continue with this. So the spring force is really equal to the mass times acceleration. But one thing I want to really be careful about here is that since the spring force is directed to the left, and we should really be thinking about, when our position is to the right, spring force is to the left, we've got a few different things that have direction, so we should be careful about positives, negatives. So I'm going to just call that negative Fs. Now our spring force formula is going to be negative Kx, back if we're thinking about Hooke's law. And then that's equal to the mass times the acceleration. And I put acceleration in there in parentheses because I don't really want acceleration in my final value or my final formula, because really it's not in my equation. So I'm going to try to come up with some way of getting rid of that. Now, since we're all the way at the end and we're at the amplitude, we're at the location where our maximum acceleration is. So we can actually use this formula we came up with before for the maximum acceleration to plug into that for acceleration. Now remember, because the acceleration and the displacement are opposites of each other, the acceleration is also to the left, and so I'm going to have to make that negative when I plug that in. So I've got negative omega squared x naught is equal to negative kx. And I put those negatives in there just to kind of really think about the directions. Now, because the force is to the left and the acceleration is to the left, they're both negative, so we can actually get rid of those at this point. It's just really important for us to think about the fact that those are both negative. Now, one thing I also didn't really clarify is when we're looking at this kx, that has to do with the location that we're dealing with in the picture. So if it's brought all the way over to this side, that's really at x naught. It's brought to its amplitude. When you release it and let it go back and forth, it's not going to go further than that. So this x naught is really the same. And that'll also let us cancel out that now. So we can get rid of that x naught and that x naught. It simplifies pretty nicely just to k equals m omega squared. And a lot of times the way that we'll write this is we'll say that omega squared equals k over m. And that's actually pretty good to know. It's not our final formula, but I would suggest you add that to your data booklet somewhere, maybe down there with the pendulum and the mass and the spring, something towards the bottom. That's definitely a good thing to remember. So I'm going to keep going with that because there are a few other things we need to do before we can get it to the period formula. And so I'm going to continue this over here just because I do like that stopping point, is that we also have this omega equals 2 pi over t. And that actually looks pretty similar to what we've got in our final formula. We've got a t, we've got a 2 pi, so that would be a good thing to plug in for omega. So for omega, I'm going to plug in 2 pi over t. And now that is still squared, and that's going to be equal to k over m. So it really won't take much simplifying because we're trying to get a formula, trying to get an equation for t. So I'm going to take and square root both sides. So we've got 2 pi over t equals radical k over m. And to make this a little bit quicker, we really are trying to solve for t, so it's easier to just flip both sides of the equation. You could go through a little while of cross multiplying, but this is a little bit faster. We take t over 2 pi, and then flip the other side, m over k, keeping that square rooted. And then it's just the last step is just multiply both sides by 2 pi. And so our period for a spring mass oscillator comes out of thinking about Newton's second law and then those forces that are applied there. And that's how we get to that spring mass formula, which you should definitely make sure you know what that is, and also how we got there. So this is our final equation for the period of a mass spring oscillator. Now the last thing that I want to look at in this lesson is the maximum energy for a spring mass oscillator. So we've looked already at our maximum position, maximum velocity, maximum acceleration. We've looked at where these are at maximum and minimum. And so we just need an equation now for the maximum energy. And I want to look at this actually in two different ways. So let's start by looking at the kinetic energy. So if you think back to our kinetic energy formula, kinetic energy for any moving object is going to be 1/2 mv squared. And again, what we were saying is we're really looking for the maximum kinetic energy, and that's always going to happen at the maximum velocity. So I'm going to take, instead of v, I'm going to plug in our formula for maximum velocity, which is omega x naught. We're going to make sure we're squaring that. And if we take that maximum value, we're going to get 1/2 m omega squared x naught squared. And you might also see that I'm actually giving the kinetic energy formula, but that looks a lot like this ET formula over here. It's the total energy. But that should make sense because when the kinetic energy is a maximum, we notice up in that chart above that there is no potential energy. So when the kinetic energy is a maximum, that is the total energy. We could also look at this with the potential energy. So if we look at EP, but again for a spring, that's the 1/2 kx squared formula that we have. And we think back to our topic on mechanical energy, we should remember that. It's also a little bit further up in the data booklet if you want to take a scroll back and look at that. But if we look at replacing this, there's no k in our final value, and the maximum potential energy happens when you're at the greatest amplitude. So I'm going to change this right away to just x naught, because that's where our maximum energy is. But where we're going to get that k from is this formula we just talked about up here. So I'm going to rearrange this and plug it in for k. And so we really have m times omega squared. And then that's an x naught squared. So get rid of that arrow. And that simplifies pretty easily to the same thing we just had. So EP is 1/2 m omega squared x naught squared. So no matter which one of these you look at, whether you're looking at the kinetic or the potential, those are just exactly the same. And that's because, again, our total energy, or our total mechanical energy, is the kinetic plus the potential energy. And when one of them is a maximum, the other one's a zero. So when you're at maximum potential, your kinetic energy is zero. If you're at maximum kinetic, your potential is zero. And so those are always going to give us the same total of just what that potential energy is. And that's where we get our ET equation, which is 1/2 m omega squared x naught squared. So again, you should make sure you know where that is on the data booklet. And there is one other one here for kinetic energy at any specific location. We'll get into that in a different lesson. But today's lesson was all about maximums and the different locations where those happen. So I hope that helps you understand the types of energy we can see, where things are maximum, minimum, and how we identify those locations on a graph. There are a couple questions to look at on page 359. Have a great day.